Good. Our speaker today in the Green Series is Professor William Calvin. I was privileged to work with Professor Calvin during a recent study on energy for the next 1,000 years for the Foundation for the Future. I found Bill one of the nicest and most committed human beings I've ever interacted with. Bill has been a professor at the University of Washington since 1966. His major field is psychiatry and behavioral sciences. He's a fellow for the Association of Psychological Sciences. Bill has been writing books at a rate at which most of us write research reports. He's written 14 books, the latest of which is entitled Global Fever, and he's going to lecture on this topic today, warming and energy, appropriate for the Green Series. The charts are extremely convincing, and I think you're in for a treat. Bill?
Thank you all. Retrieval here. That's the picture that we enjoy in Seattle of Mount Rainier, 55 miles to the southeast. And as you may have heard, the forecast is that the mountain glaciers around the world are going to be gone. You know, not the ice sheets, but the mountain glaciers. And so we're sort of looking at this as an end of summer picture after the snow's gone. There won't be any permanent ice, left there. We could always rename it, I suppose. But what I want to talk about is the kinds of damage we're in for from global warming. Because there's a lot of things about climate that change. Most of them are traceable back to global warming, but one of the reasons to call it climate change is that there's just a whole suite of things that have been going on for the last 50 years at least, and we're just now beginning to realize it. For example, there we go. The earliest computer models said something about there's going to be less rain in the Mediterranean, there'll be more rain at the northern end, and the European rivers indeed have had increasing flows over a few decades up here. And you've probably all heard about the drought trouble that the Mediterranean's getting into. So there is going to be some point in the middle here where the rain stays the same, but it's not going to be much comfort to them because it will come with more droughts and more floods. It's really the shifts that do, the extremes that do the damage, it's not really shifts. So I was speaking to a more general audience last night that I didn't want to inflict fever charts on or computer models, so I just said, let's go through the evidence for climate change, ignoring the issue of temperature, and just extrapolate what we see to whether there will be trouble ahead or not. So I'm going to go through high winds, floods, wildfires, drought, and ice melting. This is a picture you might recognize from 2 summers ago, just south of Japan, 3 hurricanes at the same time. You know about the one that went across Burma. Here's a nice picture of Burma from April 15. The mouth of the Irrawaddy here, the track went right across here. Here's Rangoon. So this is the May 5th view of the thing. You notice how much flooding there is down here. And furthermore, Rangoon doesn't really have a lake next to it. So you can see the amount of, this is all storm surge. This is due to wind strength. The counterclockwise rotation simply blowing a lot of water onto the land. Now, this is a plot just for common shipping routes across the oceans, but it goes back to 1950 or 60, 50. Just showing you the wave heights and the trend in them. This is the trend per decade. And you can see there's a lot of areas here, the higher latitudes, that have very significant wind strength changes. And of course, there's always the interesting events. This one is about 6 blocks north of Bill Gates' house in Seattle, and that's a garbage truck that got blown over. That's not Bill Gates' car. He drives a Lexus, I think, but this gives you the general idea. And you don't even have to go to the scientists to find out what happens for wind strength damage. Go to the insurance companies. And so you ask the question, if wind speed increases from 50 to 60, a mere 20%, what do you think the insurance claims do? Well, maybe you should figure out that kinetic energy is going to go as v squared, so it might go up 44%, but no, it goes up 500%. 6-fold increase in claims. So that's the kind of nonlinearity have to think in terms of. I was showing this to a group of art people last night and sort of got to this point and say, no, don't admire the brush strokes. This is really a researcher's picture out of an airplane window. And here now we see the evidence of what an out-of-season heavy rain caused in the Seattle area, just down below Olympia, last fall. Submerged I-5. These are the number of major floods per decade. This is out of the IPCC report. And basically, these are the number of major floods in the 1950s, 60s, doubled, 70s, doubled, 80s, doubled, up to here in the 1990s. And it's not just the Americas. Same thing's true for Europe, Africa, Asia. So this is not just regional climate shift. This is a global phenomenon. Same thing's true for fires, except let me show you agricultural fires before I get to wildfires. This is the MODIS instrument that you may recognize. Each dot is a fire sometime in a 10-day period. And it's just marching through the months here. But you can see how much fire there is up at high latitudes here in Siberia. Just look at that source of black soot for the Arctic. And this just shows you the number of wildfires per decade. This extreme jump in the 1990s. Europe, Africa, Asia, Australia, New Zealand. So the trend has been sharply upwards everywhere. This is just the western US, and it's the spring-summer temperature correlation here. So here's the number of wildfires going up and down, but it's really very tightly correlated with what the spring-summer temperatures are like. Basically, fires get started for whatever reason, but it's a question of whether they spread or not. And that's very much a function of whether you've baked the ground. Speaking of which, you all know about the drought-caused shortages that in the last 52 weeks, as of a couple of weeks ago, rice up 134%, wheat up 64%, corn at 68%, soy 76%, and that's before the Burma hurricane. So here's the U.S. Drought Monitor showing the troubles you all have been having here, all through the Deep South, plus here. You might notice I've labeled 32 degrees from the equator here at the southern border, and that falls about right here and about right here. Just above 30 degrees is an interesting case around the world. But the real reason I showed you this is just to remind you that of the 5 stages of drought. The top 2 are called extreme and exceptional, and that's the red and the dark red. That's all that's being plotted on this. So this is the percent of the world land surface now in drought. And it was hovering right around 100, about 10, 11%, as you'll see here. So about the time of the El Cajon eruption in '82 and the big El Nino, 82, 83, the drought area doubled. It was only obvious in retrospect. It didn't come back down, and to the data in the study that ended at 2000, I've added their more recent stuff over here. So you can see we've been up above 30%. And we have really no idea about where this is going. The models do predict a lot more. There's a question of whether it's a level or whether it's doing that. Now here's one of the reasons. The tropics are widening. That is, typically hot, moist air is rising from the equator up to this border might be about 22 degrees from the equator. And the air is coming down dry, having lost its moisture on the way up. And those form some of the zones, the zone where some of the equators, most of them, are located. So this is where Patagonia is, this is where the Kalahari is, up here we've got the Sahara and so forth. Now, the tropics are widening, and that's pushing the dry zones further away from the equator. So there's a lot of trouble occurring between about 30 degrees and 35 to 40 degrees from the equator in regions that have a Mediterranean climate. And these are regions which they're right on the border of the dry zone, and in the summertime they share the dry zone's aversion to having any rainfall. But in the wintertime, with the sun in the opposite hemisphere, low pressure systems from off the adjacent ocean manage to move eastward and give them their characteristic, winter rains but summer sunshine. And those are the areas in red, the whole Mediterranean, but also the Western Cape region, Western and Southern Australia, Central Chile, and of course up here, California. So as the tropics are widening, these regions are getting a lot drier. And that's got very serious, there's going to be a lot of population movement out of North Africa, for example, and out of Southern Europe. There's also some vicious cycles around. I want to just show you some examples of ice albedo feedback, and I left out a slide here that I was going to show you, which is simply a maple leaf sitting on top of snow, but it's indented the snow about 1 inch. And that's because the leaf is dark, absorbs energy that would be reflected back out in space otherwise. In general, a snowy surface that's fresh, nice powdery snow, reflects about 90% of the light back out in space, so what heats up things is only about 10% of what came in. Let it warm up for a single afternoon, and the surface now turns gray, or grayer. And you reflect back about 70% instead of 90, so the amount of heating of that area triples just in 1 day. Furthermore, in the oceans, where you start getting these big dark patches of open ocean in the leads, that heats up a lot more, and of course then eats into the, here, now you can see the penguin. You can see that the penguin has also been darkening the path considerably. Shows you that penguins are an agent of global warming. Okay, and you've seen this one. North Pole here, and that's last September's sea ice. The golden line shows you about where it was in 1990. It's the average of 1979 to 2002. Now, this is the actual and the computer models of how that Arctic floating ice was going. Computer models were made, of which the red line is the center here, and the bands here just show you the variation. And things were going down in the 15% level here until a few years ago when they did this. And now that precipitous drop is well outside the most band of the most extreme models in the direction of saying it was coming sooner. So this is about a 35 years ahead of schedule kind of thing. And of course, to scientists, this is sort of exciting news. That is to say, the model's obviously missing something. You've got to go hunt to see what it is. The verdict's not in. I would bet on soot from those forest fires, but and agricultural fires. So, just to remind you, we've had a whole series of things now where the trends are really pretty clear. It's pretty clear that we have to do something about it. And it doesn't really rely upon the validity of temperature measurements. It doesn't rely upon whether the GCMs accurately predict the future, or any of the kinds of quibbles that get raised about this. The records now that have been assembled really speak for themselves pretty well. But of course, it is getting warmer in addition. That is to say, the 2003 heat wave killed excess deaths of about 35,000 for those weeks. And this shows you the sea surface and land temperature trends. So you can see they're a bit intertwined until 1975, when land temperature starts growing quite a bit faster than sea surface temperature. Now, sea surface is about 70% of the globe, so the global mean temperature is sort of between them, about a third of the way up. And global mean temperature is what's plotted here, and that's the number that you always encounter in these discussions. Now, it shows you there's an upward trend for 150 years, this red line, and then a most recent 25-year trend that is 4 times steeper. And the models suggest that it's going to go steeper than that. It'd be more like 0.3 of a degree per decade. That's 3 degrees C by the end of the century. And the ecologists that have studied the vulnerability of ecosystems say now that only about 30% of the impacted ecosystems can adapt fast enough. And in forests, it's even worse. It's only about 1 out of 6 that will adapt fast enough. So there's going to be major, major disruption from that alone. Okay, let me tell you a little bit about what the models and the IPCC reports say, basically. With a 2-degree fever, which is predicted for mid-century, lose all those mountain glaciers, all the coral reefs from just heating, not acidification, and create enough climate refugees to trigger resource wars and probably genocides. Now, as it happens, we had an increase in temperature in this ballpark 125,000 years ago. It wasn't due to a global warming, it was due to hotter summers and colder winters in the Ice Age astronomical cycle. But we do know that a 1.6 degree global fever would take Greenland up into the local temperature range, which is about 3 degrees there in Greenland, that produced a 6-meter rise in sea level. So let's take a look now at, well, let's see. Okay, well, we'll get to the sea level stuff in just a second. you all remember the tortoise and the hare. It's this great Aesop's fable that told of the race between the tortoise and the hare, and of course the hare got out in front promptly, but then took a nap, and the tortoise diligently plodded past and won the race. Now, unfortunately, our race is a finish line sort of for a fast descent into hell. The hare jumps and naps, but the tortoise's progress is slow and sure. And, basically the IPCC reports are telling you the tortoise part of it. They decided they couldn't speak very authoritatively about the jump part of it. And so they stuck to the things that were pretty slow in study, and they're bad enough. So this sort of a tacit assumption that the hare conveniently is going to take a long nap when the hare is abrupt climate change is probably not a safe assumption. We've already seen what happens with drought, that sudden step up in 1983. And there's another one I'm going to show you in a minute. And in fact, the Amazon is sort of in this kind of condition. Sword of Damocles hanging by a single horsehair, threatening whoever is on the throne with an emergency. This is the Amazon basin at 4 different times near the last big El Nino, which was 97, 98. And the blue here is showing you the available watered plants, or what their roots can access, which goes much deeper than was originally thought. And so this shows you that in the beginning of the El Nino, in fact, the areas that were in drought were just up in the foothills of the Andes, plus this region over here and here. But in El Nino, you get high pressure systems over both the Amazon and over Southeast Asia, drying them out. And so you can see a progression here of areas that are getting dry. And this shows you just 3 years ago what it was looking like even without El Nino. It's been getting much drier there. This is just a more detailed slide for after the 97, 98 El Nino had quit. And this sort of shows you the terminal condition of it. Basically, all these brown areas are regions that are flammable or very flammable. So green is rainforest. That you start a fire there, it can't go very far. But these other areas really are capable of burning down. All the little red dots are agricultural fires, just as before. That's the MODIS instrument data superimposed. Those are mostly the farmers clearing their fields. Instead of letting cattle graze on the remains, they want to get a second crop instantly. And so they put it all up in the air. So if this is the condition after a 1-year duration El Nino, and this just shows you the Central Pacific temperature that's used as an index for El Nino. Anything that gets outside of a half a degree is called either an El Nino or a La Nina. But here shows you a 1972-3 2-degree episode. This one is even bigger at 82-83, and here's the 97-98. Now notice that all of them quit within 1 year. But there are plenty of smaller ones like this that last 2 years. And so the real issue is a double duration, but big El Nino. If that happens again, how long will the Amazon last? How long will Southeast Asia last? Well, this just shows you my sketch of the current situation down here is that without El Nino, we're going up almost 2 parts per million of CO2 per year. If you burn off the Amazon, or burn part of it and the rest of it rots, puts the CO2 in the air a little bit slower, but over some period of time, you jump up 40 parts per million. Now, the current excess over the typical ice age maximum in CO2 at 280, we're already up 107 above that. So if, that's just why I'm calling excess CO2. So this is about a 40% increase in the excess CO2, and surely have climate problems, except it's probably nonlinear in addition. So here's that 40% increase. Furthermore, having eliminated all those leaves, the CO2, the carbon put in the atmosphere that normally causes a 2 part per million bump will now cause a 3 part per million bump. So things will get worse even faster after that happens. This will also be a major extinction event. I asked E.O. Wilson about it, and he said about half of all Amazon species will go extinct from this, perhaps not instantly. Some of them will dwindle down because of lack of habitat, but I mean, these are 3 of my favorite species from the Amazon. Now let's do sea level. This is what Greenland looked like. Instead of having ice all over it, it melted about half of it, and this is the remaining part at 125,000 years ago. That took a 3-degree local warming to accomplish. That's what a global warming of 1.6 would do, because you sort of double for the higher latitudes. So let's just take this, a 6-meter rise, 20 feet, 2-story beach house. Here's what it does to Florida. You should think 15 million climate refugees, because except for Orlando, et cetera, they mostly live on the coast. And, the white dots here are people. That's showing you population density. And the pink here is underwater sites where people were before. This is what the Gulf Coast looks like, and the East Coast. So notice down here in North Carolina, the incursion is about 95 miles. And up here, of course, it's maybe only 75 miles or something. So Chesapeake Bay gets about twice as wide. And up here in Washington, D.C., it makes it there too. I mean, after all, this is the tidal basin. So we can always ask what a 6-meter rise does to this place. I say it gets under the security fence of the White House. It laps the steps at the back of the Capitol. It does away with all those nice museums. And it's only the stuff on the north end of Pennsylvania Avenue there that stays present. So, I mean, that's what will happen if Congress and the executive continue being unable to face the reality. Now, the Corps of Engineers could build something, I think, that would, sort of like New Orleans, protect against this. But the East Coast and Gulf Coast combined with their low slope have about 12,000 miles of coastline to protect. And the thought of building seawalls to protect 12,000 miles of coastline would, the sheer amount of cement that would be required would cause a big CO2 increase all by itself. The real scale of human tragedy is probably in Asia, because there's river deltas that have so much low-lying land and so many people. Bangladesh has 144 million citizens in a space that's smaller than Iowa, and about half of that area will be underwater with a 6-meter rise. So I mean, you're talking about 70 million climate refugees there, and with the adjacent countries not all that likely to welcome them, having problems of their own, I mean, here's the Irrawaddy Delta in Burma again. The Mekong Delta is particularly vulnerable even to the early stages. The Yangtze and Yellow River plains up here together have estimated to have about 93 million people. So the scale of people getting up and moving elsewhere is going to be considerable. And when that happens, you get something that sort of looks like the four horsemen of the apocalypse. As say, famine kills a lot of people, pestilence, plagues and such kill a lot of people. War, as to say, the organized invasion of another country. And the fourth is usually labeled death, but it's sort of redundant. And so I just label it as genocide to encompass a whole series of things that happen when cooperative groups, the one that's in power tends to get fed much better than the ones that are in minorities. And it will be a bad time to be a minority of any sort. That's the kind of thing that is, I think, in store for parts of the world where climate changes hit hardest. Now we get into the what to do issue. I tend to think there are quite a number of things that we can do, and we're not going to get out of it unscathed, but there are quite a number of things that are possible. And we'll only have to look at the past a bit to see that things that have succeeded. This is just the electricity use per person in the United States. Back in 1960, when I was an undergraduate, 4 megawatts per person, megawatt hours per person was about the annual consumption. And now it's up to 3 times that. This shows you California. Again, grew until the 70s, and then they've held it flat for all these years. So there's 35 years of successful prevention of the run-up. They claim that this has also saved about $1,000 per family annually, and the rest of the U.S. has just gone on to double. So public policy makes a big difference even when a state-level public policy has none of the teeth that a federal-level policy would have. So I'd be remiss if I didn't tell you that there's a serious issue here that I don't think anyone really understands, but it's probably, again, policy. This is that same graph as before, per capita use. Here's the average, here's California. But this shows you all the other states, and they're color-coded. And you'll notice that there's a couple of red ones, which happen to be the states that voted Republican in 2000 for president, that are down here below average. And there's a couple of states that are above average and amongst the ones that went Democrat, but pretty well it sorts by this funny thing, and I suspect it's something like this, though I'd really take a PhD thesis for someone to try to sort these things out. This may, in fact, reflect different attitudes towards using public policy. But certainly California is a good example of how you can succeed. The things to try, you've heard about new style coal plants because the industry likes to advertise them. There are 2 problems with them. First is even the industry itself says it's going to take 25 years of R&D before they produce a plant. And nobody is claiming that they will be in widespread use before about 2050. So this clearly is not operating on a very fast time scale. The other thing that people really don't mention is there's a 40% efficiency hit. And guess what that means? You have to mine 2/3 more coal. You have to have 2/3 more coal trains to haul it around the country. You have 2/3 more pollution that isn't, captured from going up the smokestack. Carbon capture and storage has this additional problem that we talk about, which is it really safe to store stuff underground? But I think that my crystal ball on this says that this isn't going to do enough soon enough, and in enough places. There'll just be too many places where people will be, the science will really be uncertain as to whether it's safe to store it that way. Well, let's go down to the next one. Transportation goes electric. Lots of ways to do that. Battery plug-in hybrids be the soonest. All electric cars with considerable range, next step. But remember that the greenhouse problems are not just CO2. They are also a series of things like methane and the nitrous oxides. Now, that means that agriculture is really just as bad a problem as cars. And I'll show you that in just a second. There's also all the efficiency arguments. I just point out that while 75% reduction in refrigerator power is really impressive, the 30% improvement in gasoline engine efficiency over the last 20 years has all been eaten up by bigger engines. Miles per gallon didn't really change with all that 30% improvement. And those are the kinds of issues that if you're going to talk about efficiency that tend to get glossed over. Okay, here's the pie chart that shows you CO2 and CO2 equivalents are about 1/3, 2/3 here. And the pie is divided by the uses that we put, the uses that produce things. So here's transportation, and that's a 14% of the pie. Here's agriculture, another 14% of the pie. Now, this in part is CO2, because if you till the soil, you speed up decomposition of it. And so the traditional methods of tilling soil are adding to the problems. But you also have all of the cattle, all the methane they produce by using anaerobic digestion, all the droppings that go on to produce CO2 and methane, and the wastes are really very substantial. So all those things contribute to this 14%, and they're all, capable of being improved considerably. For example, methane has a half-life in the atmosphere of about 6 years. Now, for CO2, it's about 200 years. So you can see that if you want some quick effects, cutting down on the methane releases into the atmosphere, buys you something much sooner, than the CO2 efforts. But the other thing that's big here is this land use change, and that's basically cutting down forests and removing leaves from their CO2 sinking purpose. And so together, agriculture here is nearly 1/3 of the pie. There's a 3% waste from dumps and such up here. So these are all things that are capable of being tackled. This is one that I like to point out. These are sort of the electricity use at 3 in the morning, and it's going into lighting up a lot of intersections all across the country. Now, clearly, because of the nature of the way baseload works, you don't want to be changing the power output of really hot stuff like nuclear reactors and coal plants, because the thermal stresses would wear them out pretty quickly. So they really want load at night, to keep this going right. And very cheap electricity contracts to municipalities is one way of doing it. But clearly, this is electricity available to recharge batteries and other such things for transportation. I mean, you just have to put your street lights on motion detector switches that serve the purpose. So we have plug-in hybrids. The hydrogen cars, again, if the hydrogen is produced by electrolysis, so with clean sources of electricity, then this is clean. But the favorite way of producing hydrogen is to use natural gas. And then there's the air car that the biggest car manufacturer in India is starting to produce. They're going to produce 6,000 of them. This is a piston engine that, instead of exploding something to increase the pressure, they just put in a whiff of compressed air to drive the piston. And at night, you hook up an electric motor to this and run it backwards, and you recharge the compressors. I like this technology because I can see developing countries able to have their own transportation industry without importing a lot of expensive parts like batteries. It also comes with free air conditioning because this engine gets cold in use. And so all those tropical countries, free air conditioning would be a real attraction. But our problem is that we have got to do a lot of things very quickly for a few reasons. First of all, if you want to avoid a 3-degree fever, you pretty much have to turn things around in the next 10 years. And furthermore, you don't have to this is net carbon release per year. We're about 9 gigatons per year now. But we have to turn this curve around and haul it way down. So we have to get into the territory here where there's net sinking of carbon by an amount that exceeds continuing production. So it's only when you get down here that you start getting any relief at all from the climate problems. Everything that's been talked about so far is about slowing down the development of the misery. It has not been about solving the problem. And it isn't until you get a good way of taking the excess carbon out of circulation, so it's not part of the circulation cycle between Earth's surface, ocean surface, and atmosphere. So only when you get rid of some of it, like sinking it to the bottom of the ocean, that you are actually going to improve things very far. Now, there's some ways of taking the carbon out of the atmosphere. You could plant more trees. But besides the issue of enough places to plant more trees and enough water for them, we have a drought forecast. We have a fire forecast, as you've already seen. No one should count on this to solve our big problems. We could manage the ocean to sink more CO2, the iron filing kinds of stuff, but we unfortunately don't know the carbon chemistry of the ocean anywhere as well as we know it for the atmosphere. There are wave-driven pumps that carry surface waters down to the depths, and vice versa, that are possible. I'll show you a slide in a minute. Artificial photosynthesis burn biomass and capture and store and sink the CO2. So like the coal plants, but it's biomass now. And finally, you could seal biomass away for 100 years in landfill kinds of situations. Here's the wave-driven pump that somebody patented a few years ago. The buoy here just rides on the waves. It's a flexible tube, and it's just got a flapper valve at the bottom and a weight ring. So as it sinks, the flapper valve opens, and that in turn forces water out of the top. So, and then, when the wave starts going back up, that closes, and you're hauling the whole tube back up. And so this is a way, depending on the wave heights, of pumping deep water up to the surface. And you can run it backwards. You can put the flapper valve up at the top, and you can sink surface waters in this fashion. So, I mean, these have been played around with. People have discussed, having whole fields of these cooling surface waters in the hurricane alleys that are coming into the Caribbean, or protecting the Gulf Coast by putting a cool zone of water offshore, have all been sort of raised by people. But we need a big effort up front for at least 3 reasons. First, we're already in a danger zone for lurches, like that step up in Drought or burning off the Amazon. And that's, to me, the big reason we have to back up very quickly. Secondly, we need to make a lot of progress up front rather than later. The reason for that is you don't want to get caught in a situation later where you don't have enough maneuvering room when something happens. It's like the pilot's problem of stalling on takeoff. Your usual dive maneuver to gain airspeed doesn't have enough room to operate. That's the kind of situation that we need to insure against by making a big progress up front. The third reason is that the climate models now have demonstrated that if you could turn things around by 2016 to 2020 and come down, you can hold it below 2 degrees. If you don't turn it around until 2040, you're in the vicinity of going up 3 degrees.